Hello, I am Nasser Al-Bonan. Today, me and my group mates will talk about our senior design project, which is the Digital Music Synthesizer project. Next slide. Here are the names of the group members. Our group consists of 5 EE undergraduate students. So, firstly, what is our project? Our team is working towards a project of creating a digital synthesizer where we can modulate the frequency of the input signal to enjoy different tones, which in our case is the piano tone at the output. So how is it implemented? We used a microcontroller, which is the Atmega 328, to operate at 5 volts at VCC pin 7, and it produced a voltage of 4.5 volts at AVCC pin 20. The microcontroller read the analog signal in the AVCC pin, which is varied in the range between 0 to 4.5 volts by using the first potentiometer for frequency modulation. By using the tone function, these values later will be divided into 89 levels of voltage, which will be mapped into 89 notes of frequency, where each note is mapped to a specific frequency value. After that, we outputted the signal tone with that frequency range and also with a 50% duty cycle at certain pins of the microcontroller. We also added another potentiometer for the volume control, which will modulate the amplitude voltage level of the output signal so that we can control the volume of the sound.
The user requirement table is shown below. For the power supply, the priority level is 4, since it is needed for the providing the device with 9 DC voltage. For the 8 mega chip, the priority level is 5, because it is used for ADC and DAC for the system, and it modulates the frequency and amplitude of the input signal. For the Arduino IDE, the priority level is 3, since it is used for displaying the waveform of both the frequency and the amplitude modulation on the IDE serial monitor. For the C language, the priority level is 5 because the IDE compiler uses C for writing code and debugging. For the modulation controls, the priority level is 4 because the frequency and value control are important for the system. By adjusting the potentiometer, the signal of frequency and amplitude can be adjusted. For the circuit component, the priority level is 3 because it is needed to construct a design for power system, power supply circuit, microcontroller, oscillator, and so on. For the documentation, the priority level is 1, since documentation describes design so that it can be adapted or used in other design. For the affordability, the priority level is 3 because components and the print circuit board cost less than $25. The project has low cost, so it is possible to adjust the consumer. For the audio output, the priority level is 4. The audio output operates as an extremely powerful on speakers.
In the beginning, we planned the base of our circuit design by using KiCad to build it. Here is the displayed picture of our final schematic diagram. We started by adding the main components of our circuit. As you can see on the top, our circuit is supplied by a 9 DC volts power supply, which is supplied by a 9 DC volts power supply, which is connected to a rectifier diode to make sure that the current goes in one direction. And it is connected to a voltage regulator to make sure the voltage maintains its certain level and to adjust the voltage provided by the power supply and later inputted into the microcontroller. 2 capacitors with a capacitance of 100 microfarads and 10 microfarads are connected along in order to enhance the transient response to prevent the regulator from oscillation. In the core of our design, you can see the Atmega 328P, which is our microcontroller. A clock frequency generator, which is quartz crystal, is connected to the microcontroller in order to generate a steady clock signal or square wave signal into the microcontroller. The capacitors with a capacitance of 22 picofarads are connected to the oscillator to help in removing the small AC signals from the generated oscillator signal. And in order to control the generated frequency and amplitude, we added 2 potentiometers, where one is for the frequency modulation and the other is for amplitude modulation. The output pin of the amplitude modulation is connected to pin number 5 of the microcontroller, and the input pin is connected to the audio output pin, while the output pin of the frequency modulation is connected to pin number 20 on the microcontroller, and the input pin is connected to pin number 22 of the microcontroller. This is our PCB design after adding the traces in order to check for any errors in the circuit design. We connected each component in the correct position and used the front and back layer of the PCB board to have enough spacing between each trace and to prevent overlaps between them, and also to prevent short circuits that may result in damaging the components or even the whole board. This is a 3D view of our PCB design. As you can see, all of the components are placed properly with good spacing between them. It is clearly shown that the traces are not overlapping and have enough spaces between each other. Mr. Mark Bruno in the SDSU lab kindly offered to build the PCB for the senior design groups. So we sent him the Gerber files later in order for him to construct it. And this is the case wiring diagram of our project. This was designed to know exactly where the external components will be connected on the PCB board. The external design of the device will include a power jack for the power source, as well as an audio jack for the speaker that is used to test the outputted tones. More so, it has two potentiometer knobs, where one is used to control the pitch and of the sound in order to change the frequency signal, and the other is used to adjust the volume of the sound.
For our enclosure design, we designed it using SolidWorks program. As we can see in the schematics on the left, we have the dimensions of the music synthesizer. On the right is the 3D view of the music synthesizer enclosure design. In the image below is a physical description of our music synthesizer. We have added 0.1 inches as a space between the enclosure and so that the PCB can be fitted perfectly inside. As we can see, there are two potentiometers on the top. The first one is for the volume control and the second one is for the frequency control. And on the side, we have an input port that is connected to the power supply going through a 9-volt DC adapter and an output port connected to a 3-ohm speaker.
So here's the block diagram. So we have 5 voltage input signal. So this input voltage signal will be varied by using a potentiometer for the frequency modulation, and then go through the analog to digital conversion. After that, we have the signal will be modulated its frequency process, and then we're going through the signal output. We're going through the digital to analog conversion and after that, the output signal will be varied by using the potentiometer for volume control at the output to the speaker 3 ohm. This is the engineering specification. The requirement that user would have is the output voltage at the regulator. It should be 5 volts DC, and the power for operating the microcontroller at Mega 228 is which is the 5 volts DC. The input analog voltage at the AVCC pin is the 4.5 volts DC. This yes, the next one. Another requirement is the output analog signal at the volume control. We expect to have the output voltage at the amplitude control in the range from 0 to 2.5 voltage. The frequency range of the output analog signal at the volume control, we expect to have 27.5 to 4,378 Hz. The potentiometer resistance is start from 0 to 5 k ohm. And the short circuit ground fault also needed. We need to make sure that there is not any hot wire touching to the ground to avoid the ground fault. And the PCB size required to have 4.5 inches multiplied by 3.5 inches. Testing by using the measuring tab. The PCB connection, audio, and the power jack connection. Make sure that all connect to the PCB and are operating well. The component cost must be under $25. And this is the firmware specification. We need to set up the IDE compiler which will be connected to the Atmega microcontroller. We then start the mapping the input analog from 0 to 4.5 volt DC to the input value level from 0 to 1023 by value. So we have total 1024 input value. After that, we divide again this 1024 input value voltage into 89 level of input voltage. Then we mapping these 89 levels input value into the array of 89 piano key frequencies. So then we set the duty cycle to 50%, set the note duration to 95 milliseconds, and the delay time to 70 milliseconds to avoid thick noise happen between the note duration. Finally, we write the output value to the frequency pin PD3, then debug and compile the code. And you see over here, we had a formula for the frequency of the piano key, which is Fn equal to 440 multiplied by 2 to the n minus 49 over 12. So every note of frequency K will be calculated by using the formula. For the validation procedure and the result, firstly, we're testing the operating power for the Atmega 328. So I'm using the Clone Tool MM100, the device multimeter. I applied the positive probe into the output of the capacitor at the regulator. And I applied the negative probe to the ground. So the display in the string, we have 5.04 DC voltage. And I use the same method to testing the VCC pin number 7 at the Atmega 228 and the ground. We have 5.03 voltage DC, which is very close to the expected value of 5 voltage DC for operating the system. So in this test, we pass this. And this is the testing for the input signal for frequency modulation. So I apply the same method and the same multimeter device. And at the AVCC pin number 20, I have 4.23 voltage DC. And the expected value, we should have 4.5 voltage DC. This is very close to the value that we expect. And this 4.5 voltage DC will be used as the input signal for frequency modulation. Since this is slightly different, so I think that should be good. And then for this test, we pass it also. Next is the output signal and the volume control. So for this time, I'm using the Clone Tool MM700 device multimeter. I use the same method to testing the output of the volume control, and for the negative, I applied it to the ground. And by playing the knob of the volume control, when I turn the knob to clockwise direction, I hit to 0 voltage DC. And when I turn the knob anti-clockwise, I hit 2.478 voltage DC, which is very close to 2.5 voltage DC as we expect. And with 50% duty cycle, so that's why the output of voltage at the PWM PD3 pin number 5 will be only 2.5 voltage DC. The test is good because it's close to the expected value, so we passed for the test. And this is the frequency range at the output. So again, I applied the DMM700 to measuring the frequency at the output of the volume control, and when I play the frequency, turning the knob clockwise, I hit 32.02 Hertz, very close to 27.5 Hertz expected value. And this is the minimum frequency range that we hit. And when I turn the frequency knob to the anti-clockwise, I hit the maximum range is 4,386 Hertz, which is very close to 4,378 Hertz. I think this is slightly different. It's not affect to the output. So this pass, so this test is passive.
Here is the table of cost breakdown for the project. Most of those components are bought from Amazon and eBay. According to the requirement for the project, components listed below are required. For the diode, voltage regulator, and capacitor, the quantity should be more than the amount that is required from the project, since some of components have high possibility to get burned. We are using Atmega 328P to be the microcontroller for the print circuit board. One Atmega chip costs $2.47. Resistor costs $0.1. Since some of the capacitor are sold as a package, we decided to buy the package capacitor since it is not too expensive and the replacement of the capacitor can be done anytime if the certain capacitor is damaged. The potentiometer can be used to adjust the frequency and amplitude of input signal. Since the resistor has low risk of to get damaged, the quantity is sufficient with the quantity that is required from the project. The monophone jack and the power adapter jack are required for the power supply and the audio for the print circuit board. The monophone jack costs $3.45 and the power adapter jack costs $5.49. The crystal oscillator and the wire is also needed for the project implementation. It costs $0.7 for a single oscillator. We designed to buy the power supply adapter from eBay. It costs $1.1. The reset button for microcontroller costs $1.69. The LED indicator costs $1.14. The total amount that we cost is about $23.554.
In conclusion, many of the knowledge and skills gained during our senior design can support us in the future, especially when working on tasks with other colleagues. To be more specific, communication with other engineers will be better as ours has greatly improved while we worked on this project. Also, our experience with lab equipment will greatly aid us in handling objects in the industrial environment, as it will prevent any safety hazards while performing tasks in the future. In the rare cases of having to work remotely in the future, we believe that we will be handling it more efficiently since we worked online in this course and for the most part of the previous one. Lastly, the information acquired from working on the digital music synthesizer project in this course will be very helpful in answering technical questions in job interviews. And the most important thing in our project, that it will be useful for many inexperienced music enthusiasts who are interested in synthesizers, as it will help them in gaining more insight on how to build and improve their own digital synthesizer. And now we'd like to play our music synthesizer, so if you want to lower your volume so you can hear it. Thank you for watching, guys.
Thank you very much for watching.